Hey there, it's Shannon MATHCHICK Myers, and today we're checking out the integral test, P-series, and harmonic series. If f is continuous, positive, and decreasing for x greater than or equal to 1 and a sub n equal to f at n, then either both converge or both diverge. And so what we do here is we use the integral from 1 to infinity of f at x dx, and we use that to test the summation from n equals 1 to infinity of a sub n. Now, our interest is whether the series converges or diverges as n approaches infinity. And so the index of the summation can start at some integer capital N, as opposed to, sorry, there's a typo, n equal to 1, just as your f at x can start a little bit later than x equal to 1 as the bottom limit of integration. Okay, so how it works. Using the integral test to determine whether a series converges or diverges. So here we go. What test are we going to use? Okay. And we're going to use the integral test. And then step 2, we'll check our conditions. You're going to find that some of the earlier tests that we learn have more conditions than what happens later. And so one condition was that we needed to know, is f continuous? So the f that we're using is going to be related to a sub n. So we're going to use natural log at x over x cubed, right? And then we're looking, if you start at x equal to 1, do you see that you'll get natural log 1, which is 0, over 1 cubed? And then as your numbers get bigger, your graph is going to, there's no discontinuities. The discontinuity would be at x equal to 0 for this graph. So f is continuous on one to infinity. Now our next condition, 2, is f greater than 0 for x greater than or equal to 1. So we just saw that f at 1 was equal to 0, right? So let's take a look. The numerator is what we're concerned with, because for positive numbers, the denominator will be positive. And so the natural log function after x equal 1 will start having positive numbers. It's as you get closer to 0 that it's going to have negative numbers when you're less than 1. And so we would say f is greater than 0, so positive for or on. We'll say from 2 to infinity. So we'll start our integral at 2. Okay, third thing to check is f decreasing on I'm going to say from 2 to infinity, since that's where we're starting now. So let's check it out. F prime at x is equal to one over x times x cubed minus natural log at x times 3x squared all over our denominator x cubed squared, and then f prime at x will be x squared minus 3x squared times natural log at x over x to the 6th. Factoring out our x squared, we'll get 1 minus 3 times natural log at x over x to the 6th. We can completely divide out that x squared in the numerator, and in the denominator we'll have x to the 4th, which is always positive. And so f prime at x is equal to 1 minus 3 natural log x over x to the 4th. So now when we set f prime of x equal to 0, we can find out where this trend is. We want f prime to be negative, so we want that numerator to be negative. So here we go. If we isolate our natural log at x, then we will get 1/3 on the other side with a little bit of algebra. And then exponentiating both sides, we'll get x is equal to e raised to the 1/3. And e to the 1/3 is greater than 1 but less than 2, because remember e is 2 point something. So let's see what we have. Second, e to the 1 divided by 3, enter, is approximately 1.4, and so f is, I'm just going to put an arrow down for decreasing on 2 inclusive, infinity non-inclusive. So the conditions check out, which is exciting. And so next up, well, what's left? We need to run the test, right? So let's go ahead and start with running the test. So step 3, run the test. Okay, so what we need to do is find the integral from 2 to infinity of natural log. I'm actually going to write this as a product x to the -3 times natural log at x with respect to x. So this is going to require integration by parts, right? And so let's go ahead and set it up. So we will have u has to be natural log at x, so that's nice. Du, it will be dx over x. And then dv is going to be x to the negative 3 dx. And so integrating both sides, we'll have v is equal to negative 1/2 x to the negative 2. So considering the indefinite integral, x to negative 3 natural log at x dx, we'll have u times v. So we'll have natural log at x times negative 1/2 x to the negative 2 minus the integral of v du. So v is negative 1/2 x to the negative 2, and then our du was dx over x. So here we go. Good? Excellent. So simplifying, we will have the integral of x to the negative 3 times natural log at x dx is equal to negative natural log at x over 2x squared plus 1/2 times the integral of x to the negative 3 dx. So we'll have x to the negative 3 times natural log at x dx, almost there, is equal to negative natural log at x over 2x squared plus 1/2 times, we'll get, let's see, x to the negative 2 over negative 2, and we're not going to need the constant note of integration because we'll be using the limits on that improper integral. And so let's see what we end up with. X to the negative 3 times natural log at x dx equals we'll have, let's simplifying a bit, we'll have a negative 1 over 4x squared. We can divide out because we'll have a 2 times a negative 2 in the denominator of the second term. And then what we'll have left is 2 times natural log at x plus 1. Cool so far? Excellent. And so now we can go ahead and do our improper integral. And so our improper integral from 2 to infinity of x to the negative 3 natural log at x dx is equal to the limit as b approaches infinity of the integral from 2 to b of x to the negative 3 times natural log at x dx. Now this in turn will equal to the limit as b approaches infinity of what we found, negative 1 over 4x squared times, I'm going to write this natural log at 2 natural log at x as natural log at x squared. And then we have a plus 1. And that's going from x is 2 to x is b. And so we will get the limit as b approaches infinity of negative 1 over 4b squared times natural log b squared plus 1, and then minus 1 over 4 times 2 squared will be 16, and then times natural log of 2 squared, which is natural log of 4, plus 1. All right. They both have a negative, so let's factor out that negative, and we'll have the limit as b approaches infinity. So this first one will have the limit, but the second one will not have the limit because there are no b's in the second term. So then we'll have 1 plus natural log b squared over 4b squared. There'll be a plus sign in the middle because I factored out the negative. And then we'll have 1 plus natural log 4 over 16. Good so far? So the limit only goes to that first portion. So now this will equal to negative. If you plugged in infinity, you'd get infinity over infinity, which means that L'Hopital's rule applies. So L'Hopital's rule applies when we're doing the limit of this first term. So what we'll have is negative limit as b approaches infinity of 2b over b squared divided by 8b and then this one stays the same. This b cancels out, and that one goes to b to the 1. And so what will happen is we'll get negative limit as b approaches infinity of one over 4b squared, with a bit of simplification. And then plus 1 plus natural log 4 over 16. That's going to give us 0 for the first one, and then minus 1 plus natural log 4 over 16, which will be negative 1 plus natural log 4 over 16. So the integral from 2 to infinity of natural log at x over x cubed with respect to x converges. And the last step is our conclusion. We did all the work. So now what are we on? Step 4. Step 4. The summation from n equals 1 to infinity of natural log at n over n cubed converges by the integral test. Cool, cool? So the whole problem is your work shown for your work shown. So don't worry about boxing some final result. Let's make this a little clear that we have 2 columns. All right, so the whole process is part of it. I know it's long and it's a bit mathy, but that's okay. You can do this. All right, so we've got our integral test. So now let's take a look at the next one. All right, so again, we'll use our integral test. We'll be learning some other tests in case you're not a big fan of the integral test. So step 1, what test are we using, right? So what did I call it before? Sorry. Test. So you name your test, and our test is the integral test that we're using. And step 2, conditions. And so the first part is f continuous? For x greater than or equal to 1. And let's see. Yes, because when you plug positive numbers in here, there's all positives in the denominator and the numerator, and so there will be nothing that will zero out your denominator, because you've got things that are being raised to an even power, like n to the 4th and n squared, and you're adding everything. So we're going to say yes to, and that should have been an S, is f greater than 0 for x greater than or equal to 1. And same reasoning, yes, you've got these even integer powers that are raising a positive base to that power. So you're all good there, and you're adding everything. So we're going to say yes. 3 is f decreasing. On 1 to infinity. So for this one, we will find the derivative and of that related function. So I didn't put that down here. Our related function that we're dealing with is f of x is equal to x over x to the 4th plus 2x squared plus 1. So this is going to be a whole lot easier if we factor f of x now and later. So f of x is equal to x over x squared plus 1, the quantity squared. So that denominator can be factored. So f prime of x will be equal to 1 times x squared plus 1 squared minus x times 2 times x squared plus 1 times 2x, using our chain rule, and then the denominator is squared. So we'll get f prime at x equals x squared plus 1, the quantity squared, minus 4x squared, from the x times the 2 times the 2x, times x squared plus 1 to the 1 power, all over x squared plus 1 to the 4th. We can divide out one factor from each term of x squared plus 1, and we'll be left with f prime of x is equal to, we'll get x squared plus 1 minus 4x squared gives us 1 minus 3x squared over x squared plus 1, the quantity cubed. So that denominator is always positive, right? And the numerator, let's see when that's going to be 0. So 1 minus 3x squared equal to 0. 1 equal to 3x squared. 1/3 equal to x squared. So when x is plus or minus the square root of 1/3, we don't worry about the negative. And so the square root of 1/3 is going to be smaller than 1. So this will be x is decreasing on 1 to infinity. Cool, cool. All right, so we checked off all of our requirements, and now we'll run the test. So here we go. Okay, so I'm going to use that second version right here that we looked at, because that'll be set up for integration. So the integral from 1 to infinity of x over x squared plus 1, the quantity squared with respect to x, is equal to the limit as b approaches infinity of the integral from 1 to b of, and I'm going to do a little adjusting here, the derivative, our g prime, our g is x squared plus 1, so our g prime is 2x, so we need a 2x, right? And so we'll multiply by 1/2. So we'll get 1/2. We can take it outside that limit. And then we'll have our 2x dx over x squared plus 1 squared. That will equal to 1/2 times the limit as b approaches infinity of x squared plus 1 is being raised to the -2, and so we'll get x squared plus 1 over -1, and that'll be to the -1. That will go from x is 1 to x is b. And so we have, I'm going to bring the negative outside the limit. We'll have -1/2 times the limit as b approaches infinity of 1 over b squared plus 1 minus 1 over 1 squared plus 1. So that will be negative 1/2. When I take that limit on the first one, I'll get 0. And the second one, the limit won't affect, so I'll get minus 1/2. And then that will be positive 1/4, which means that the integral from 1 to infinity, I'll write it in the original form, x over x to the 4th plus 2x squared plus 1 dx converges. So that integral was easier, right? So now our conclusion. So step 4, conclusion. The summation from n equals 1 to infinity of n over n to the 4th plus 2n squared plus 1 converges by the integral test. Cool? Excellent. All right. So now we take a look at P-series and harmonic series. So a harmonic series is the sequence of sounds represented by sinusoidal waves in which the frequency of each sound is an integer multiple of the lowest frequency. So Pythagoras and his students discovered this relationship between the tone and the length of the vibrating string. The most beautiful harmonies seem to correspond with the simplest ratios of whole numbers. Later, mathematicians developed this idea into the harmonic series, where the terms in the harmonic series correspond to the node on a vibrating string. That produces multiples of the fundamental frequency. So 1 to 2 is twice the fundamental frequency. 1/3 or 1 to 3 is 3 times or thrice the fundamental frequency, and so on. So in music, strings of the same material, diameter, and tension, and whose lengths form a harmonic series produce harmonic tones. A general harmonic series is of the form: the summation as n goes from 1 to infinity of 1 over a times n plus b, which will be equal to 1 over a plus b plus 1 over 2a plus b plus 1 over 3a plus b, and you keep going on. You get to 1 over a n plus b and you go on from there. The harmonic series is a special case of the p-series where p is equal to 1. So this p-series looks like this. The p-series summation n goes from 1 to infinity of 1 over n to the p. So in this one, the n will change, but the p stays constant. So in the geometric series, which we worked with before, the base was constant and the power changed. Now the base changes, but the power stays constant. So this would look like 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p. And you'd keep going on, plus 1 over n to the p, plus dot, dot, dot. And it will converge for p greater than 1, and it diverges for 0 less than p less than or equal to 1. Cool, cool? Okay, so now let's, in this p series and your geometric series are very powerful comparison series, which we'll be working with next time. So it's really good to get a handle on them. So determine the convergence or divergence of the series and explain. Well, let's try our steps here. Step 1, your test. Well, we have something, don't we, that isn't this equal to the summation as n goes from 1 to infinity of 1 over n to the 1/2. So now notice it's in this format, so I know you could rewrite this as with a negative exponent, but you don't want to do that for this one because you want to have it as 1 over n to the something so you can see what your p is. So this certainly is a p series, right? And so we can skip conditions because we can write it as the correct format. So step 2, in the condition for this, this is a p series with p equal to 1/2. And so, step 3, run the test. Well, not much to run, right? P goes into 0 is less than p, which is equal to 1/2, right? Which is less than or equal to 1, right? And then our conclusion the summation from n equals 1 to infinity of 1 over the square root of n is a divergent p series. You're done. It diverges. All right? Okay, so now let's take a look at this next one. All right? So, step 1, test. Well, here what I'm seeing is that these are all being, we can write all of this as the fifth root, because you could write this as 1 over the fifth root of 1, but something else is going on. Beautiful, they're perfect squares. So here, this is indeed going to be a P series. So I'm going to write P series here. And then step 2, we'll write what that series is in our conditions. I know that these steps are a little bit of overkill for something so simple like this or the geometric, but it can help. All right, so the summation n equals 1 to infinity of 1 over n. Remember, it's power over root, so to the 2/5. So you're squaring each n, and then you're finding the fifth root of it. So this is a P series. With P equal to 2/5. So here, if you run your test, you just really take a look at what inequality P falls into. And again, it's between 0 and 1. And so that's going to diverge. And we'll put that in our conclusion. So the summation from n is 1 to infinity of 1 over n to the 2/5 is a divergent P series. Cool, cool? Awesome. All right. And that is it for today. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that subscribe button, like button. You can share the video. And sorry if I was a little bit blah today. I've got pneumonia, so doing the best I can. All right. Bye.